So the next speaker is Rémi Chevallier. He will talk about contrail observation, please.
Thank you very much. Thank you for the invitation. Good afternoon, everyone. I'm Rémi Chevallier, and I'm a PhD student. I'm starting my third year of PhD, and I work with Airbus and ENAC, which is the French Civil Aviation University. And for the past 2 years, we've worked quite a lot on condensation trails observation. So, as Pavel already introduced in the last session, condensation trails are these thin linear clouds that are forming behind aircraft flying at high altitudes in very cold and moist environments. And these contrails actually have a climate impact. The problem is this climate impact is very uncertain. And this is why we worked on contrail observation. So first of all, how does some so small clouds have such a high climate impact? So actually, contrails have the same kind of climate impact as any other type of cloud, of high cirrus clouds. It's mainly based on two adverse effects. The first one is that it reflects some of the incoming solar radiation back to space. So this is a cooling effect. And there's a second one, which is a warming effect. It traps the heat emitted by the Earth that tries to go to space, and it traps it in the atmosphere. So this one is warming. So, for example, during the night, it's obvious that you don't have incoming solar radiation, so it's only warming. But even during the day, when you have both effects, the average value of the radiation imbalance is still about warming the Earth. So we still have a climate impact that actually impacts our climate. And the problem is that these are clouds that wouldn't be there if we didn't fly in the area. And they can spread and make very large cirruses that wouldn't be there if we didn't fly. So this is the problem with contrails. So these are the two main models that I used to predict contrail impact based on weather data and aircraft performance. So you have the fuel flow, you have the amount of soot in the exhaust, these kind of things. And so these are used to define these climate-sensitive regions that we are going to try to avoid using trajectory optimization or any other technique to mitigate the climate impact of contrails. The main problem is that by avoiding these regions, you go away from the optimal trajectory. So it means that you will burn more fuel. So we have a trade-off to deal with. So this is an interesting topic to deal with trajectory optimization, dealing with this trade-off. The other problem is that these contrail-forming regions are quite uncertain. So we need to have a very accurate prediction of the climate-sensitive regions. Otherwise, we will burn more fuel and end up doing things worse than if we did nothing. So we need to do that carefully. So as you can see, so contrails prediction are very sensitive to especially one variable, which is relative humidity. And as you can see in these correlation plots between the measurements made by Mosaic Aircraft and the weather data that is used most of the time, which is ERA5. That's the one that is used in most climate impact studies. So as you can see, the relative humidity is subject to a lot more uncertainties than the other variables. So this is the problem that we are facing right now. And this is why we tried to implement some contrail observation, in situ observation, to help scientists improve their models and improve the weather forecast systems as well. So how can we actually observe contrails? So the first method that is quite natural is to use ground cameras, because we can't see contrails in the sky. So why not use machine learning to detect contrails and just study them like that? So ground cameras actually have a great temporal resolution, like that's basically 30 images per second, whatever you want. However, the field of view is quite limited. Most of the time you can only see a contrail for like 10 to 20 minutes max. So you need a large number of cameras to be able to monitor an area. And low clouds can prevent you from seeing contrails. There's also no camera over the ocean. Night observation could be a problem as well if you're using visible light cameras. So we have a lot of drawbacks with these systems. but it's cheap. Then we have the low orbit satellites. These are great resolution. The main problem is that it's only one-shot images. So this is interesting, but we can't monitor the life cycle of contrails because the time between two pictures is usually larger than the lifetime of the contrail. And then the method we first chose is geostationary satellites. So this one is GOES 16. It's like this image is from a combination of infrared channels, and it's a satellite that is over the US. It has a temporal resolution of 5 to 15 minutes according to the product you use, and it has a great spatial coverage, which means that you can monitor the whole full disk. You monitor the whole continents at once. So this is why we first chose to use this one. However, it has a low spatial resolution, which means that you need to wait until the contrails spread enough to actually be able to see them. It can take like 20 to 25 minutes in my test case. So this is a problem if we want to identify which aircraft produced the contrail. So then how do we detect on these methods? So we chose instance segmentation methods because they're able to identify individual contrails, which is not the case with, for example, Google method that is using semantic segmentation. And it also gives the shape of each contrail, like draws polygons around it. So it is still very interesting. However, it's time-consuming in the labeling process, and it needs a lot of data to train, especially when you have objects close to each other. And we also had another problem because, so at the time, there was no contrail data sets whatsoever. And even to this day, there's no instance segmentation data set available. So how did we do? So we tried to build a synthetic contrail data set, which means that we tried to generate images that are realistic enough to train a computer vision model to detect contrails. So we used the model I talked about very fast at the beginning of the presentation, which is COSIP. It's able to simulate the evolution of contrails from formation to dissipation, and can give you a few other variables, like the position, the width, and some of the radiative forcing, the optical depth, etc. And we thought, why not trying to build realistic images from these values? So as we said at the beginning, contrails actually trap infrared radiation that are trying to go to space. And we tried, so it basically acts as a mask that you put in front of a light source. So we tried to replicate the behavior of contrails, because we just tried to build a realistic mask from COSIP outputs. And this gives this kind of results. So we added somehow realistic masks to the GOES images and trained our computer vision model on these images. The main advantage of this method is that you can control absolutely everything about this method. You can put as many overlap as you want. You put as many different shapes and sizes. So this was the main advantage of this method. Then we trained our model, which is a mask CNN plus a very large feature extraction method. And it's able actually to give you these polygons, one polygon per contrail, per individual contrail, which is what we needed. The accuracy is a bit below the one from Google, for example, but it's able to give you accurately each contrail as an individual polygon. And then we built a method that is able to use the detection and then use air traffic data to track the contrails through time and match them with the aircraft that produced them, which is what atmospheric scientists actually need in the end. However, as we said, GOES 16 has a low resolution, so we can only see contrails 25 minutes after they're formed. So it takes quite a long time, and that introduces loads of uncertainties, especially because of wind uncertainties and inaccuracies in the air traffic data. So it means that we have loads of drawbacks, like a mismatch, etc. So one way to deal with that would be to add information from ground images. As we said, we can basically see contrail forming in the sky. So the matching process becomes trivial. You basically saw it happen. So this is very recent work. That's basically this week's work. And so we are trying to build a system that is able to combine information from ground images and satellite images to improve the accuracy and the robustness of the matching and tracking process. And because our method is sensor agnostic, we can already do that, actually. We can provide it with polygons from any type of observation method. It will just improve the accuracy and the robustness of the result. So that's the next step. Then, what are we doing? Why are we doing that for? So we are trying to compare observations with actual predictions. So this is a comparison between predicted contrail with COSIP and the actual observed contrail. And in this case, the model predicted the contrail formation at the wrong place. And this is a problem because if we want to avoid contrails accurately without burning too much extra fuel, we really need an accurate prediction. So in this case, avoiding this sensitive region that is not predicted exactly at the same place might mean that we make things worse than if we did nothing. So that's a problem. However, the prediction works in many different cases. So the main aspect, like the next step of our work is to identify in which condition do these prediction work, actually. So I will finish by just giving my takeaway messages. So detecting contrails is possible, and it's still subject to several limitations with geostationary satellites only, but combining it with other type of observation look promising, and we need to compare these observations with predictions to be able to identify where we can actually use the prediction accurately in operations. And the last message is that this kind of work needs loads of different sensors, loads of different methods and models. So collaborative approach between different actors of the field might be necessary in this case. So let's work together.
Thank you very much. Any questions? In that case, oh yeah, please.
Hi, thank you for the good presentation. Just curious about the ground stationary camera data. So is it open source data, or is there what is the data source?
Okay, so for the moment, so I found one data set that is available freely on it's on RoboFlow platform. So there's data set on contrail observation, and the cameras are not open source because this one is on my roof. It's basically home, but you can find some webcams, for example, on the DWD website, like the weather German weather national provider, and you can find this kind of webcam data and work on these.
Yeah, just out of curiosity, do you think is it able to use Google Map data for this kind of research to replace this data set, something like that?
Okay, the thing is, we've worked with Google on this topic quite a lot, and they've worked with OpenStreet, OpenStreetMap, and the Street View cameras. The problem is that it's very difficult to calibrate the position of the camera to say, okay, this contrail that I see on the image comes from this aircraft. This is very difficult to do. But I know that there's another actor which is called Breakthrough Energy. It's a non-profit owned by Bill Gates Foundation, and they work, and you can find the app on the Apple Store and Play Store as well. You can take pictures of contrails in the sky, and it will locate it with your phone orientation, and they will use it to improve the models in the end.
Rémi, thank you for the talk. So I just was curious about sort of your viewpoint on the next steps, where we should focus our progress. Should it be, for example, sensors for the aircrafts that are monitoring humidity? Should we have maybe cameras on the aircrafts that are looking backwards? Should we actually invest, maybe ask Elon Musk for the cameras on his satellites? What would be the things if the sky is no limit?
Okay, if the sky is no limit, okay, so Elon Musk satellites are a bit too low. So we will have the same problem as with my Landsat images, like not enough revisit time. However, like any other type of proposition could be great, like rear-facing cameras. We're actually working on that in Airbus. What was the other one again? Yeah, humidity sensors. So this is some key elements, because that's one of the main reasons we have inaccurate weather data. There's actually no sensor that is actually able to measure humidity at these altitudes. So this is one of the main problems. So definitely this is a point to take care about. But I think because we have to implement something before 2025, which is basically tomorrow, because regulation comes into action in 2025, with financial actions in 2028, we need to find something right now. We don't have any time for anything. So one thing would be to identify in which regions do we already have something that works, and in which region we can apply this without being too much of a problem for ATM constraints, for example. But then we can do something.
Yes, I have a question about the balance. Basically, you are trying to optimize for two things, right? One being formation of contrails, the other one being the fuel consumption. Could you give us an idea of what are the order of magnitude? Let's say you avoid the formation of contrails over, I don't know, like 1 kilometer. By how much are you willing to extend the flight plan?
Okay, so this is a quite tricky question, actually, because there's a study that went out last week on the topic, stating that the increased fuel consumption was like below 0.6% if you avoid all the big hits contrails, like the most impactful contrails. I don't think it's entirely true, because they use some simple hypothesis. So I think airlines won't allow for more than, let's say, 1% extra fuel. If you need a lot of extra fuel, regulation will come into play and ask you for more reserves to take care about unpredicted like trajectory changes. So by having more reserve, you will burn more fuel because you'll be heavier. So this is a very tricky question. I don't exactly have these numbers in mind, but it's okay. I give a number, but like below 1% if we like for the average value of the fleet. But for one flight, it could go up to like 15% if you choose to avoid it. In this case, it's not worth it. But
thank you for a very interesting topic. I maybe missed it at the beginning, but did you consider the altitude of the flight? And is it identify any connection between the altitude of the flight and the impact of this contrail?
Actually, yes, but it's more related to the shape of the weather, the situation, the weather situation at the moment you flybys. So, indeed, the altitude is very important, because like contrail forming regions are usually very large in terms of lateral extent, but very thin in terms of vertical extent. So it means that altitude is key. But the thing is, like according to the day and according to the weather patterns, the altitude that actually produces contrail will be very different each time. So yes, indeed, it's very important, but it's not as easy as predict.
If no questions, I have another one. You need predictions, right? And you need climate or weather models. And it's very hard to modeling. So what do you think? Are the weather model quite accurate enough, or do we have there additional work to do?
I think that weather model could be accurate enough. The main problem is that it's never been optimized to solve this specific task, predicting relative humidity at high altitudes. We don't even have a sensor to measure that. So I think that the weather forecast systems actually are accurate enough, but we just don't have the actual input data, and we just replaced some part of it, parameterized some part of it, just to simplify it and save computation time. So we just need to re-optimize these methods, and then it's going to be okay.
Okay, thank you very much.
But it takes time.